Okay, so Dalton's Law of Partial Pressures is the first thing we're going to do today, and it is a law that states that those two blanks are equal. Equal amounts of gas at the same temperature and volume have equal pressure. So write equal. I hope that I left you more room in your notes because that is not very much space. Okay? It's going to be right after Avogadro's law, which is the last law we talked about. Okay? So it states that the total pressure inside the container is equal to the partial pressure of each gas. So the formula looks like this. P total, P standing for pressure, is equal to P1 plus P2 plus P3 dot dot dot. Meaning as many partial pressures of gas as you have, you add them together. If I was doing this in an actual real problem, I actually wouldn't put P1, P2, P3. I would put like the symbol of the gas. So let's say I had nitrogen, oxygen, and helium. I would say P(N)2 plus the partial pressure of oxygen plus the partial pressure of helium, and that would be equal to P total. Okay? It's one of the easiest laws there is because we're just adding. Okay? So let's do a couple of examples. So if I had these three containers, and I mixed them all together, I could add up and see what my total pressure is in the final container, which would be how much? 6. Who said 7? So that would equal 6 atmosphere because I would simply just add them up. Now, if we are given a problem and our pressures are all in the same unit, then we're good to go. But if you're given a problem and you have two different units, you have to convert so that your units match. You cannot add and subtract pressures in different units. Okay? And usually I don't care which one unless I specifically ask for it in that particular one. So if I had given you atmosphere in millimeters of mercury and I didn't specify, you could put it in either one. Unless I said, hey, I want the answer in atmosphere, then you'd have to convert the millimeters of mercury to atmosphere. So let's do 2 quick examples because it's easy peasy, lemon squeezy, isn't that what y'all say? So what is the total pressure in a balloon filled with air if the pressure of the oxygen is 170 millimeters of mercury and the pressure of nitrogen is 620? So we're going to do P total is 170 plus 620, which gives me 790 if I am doing my mental math correct. Okay, I am recording, ladies and gentlemen. So, yeah. Okay, in the second balloon, the total pressure is 1.3 atmosphere. What is the pressure of oxygen if the pressure of the nitrogen is 720? So we're going to do P total. It's going to be equal to the partial pressure of oxygen plus the partial pressure of nitrogen. Okay? I see that this is 720 and this is 1 atmosphere, so can't do that. So I'm going to go over here and do my quick conversion. I did not know it was supposed to rain today, but apparently it is. 760 millimeters of mercury is equal to 1 atmosphere. So that comes out to, I believe, point something. I can't remember. I have it written down. Thank you. 0.947. 0.947 atmosphere. So now I can plug those into my formula. I have a total of 1.3. X is oxygen and nitrogen is 0.947 atmosphere. So I can get my partial pressure of oxygen by subtracting them, and I would get 0.35 or 343. I usually did, earlier I did this in my notes as 0.95 because that's what it would round to. Because I really only needed it in 2 because I have 2 there and 2 there. So really I should have done that as 0.95. Okay? Easy enough for that? Okay. An application of the Dalton's Law is when we collect water or we collect gas over water. Okay? And we have a lab that we would sometimes do with this. I might still try to fit it in. but Monday is a holiday for you guys, so we may have to forego because I did that other lab instead, which I felt like helped you understand the relationships of the variables. But basically, when you do this, if you see right here, when you're bubbling, oops, here we go, when you're bubbling through here, as you collect the gas, you're also going to accidentally collect some water vapor, okay? And so we have to account for that water vapor when we do collection of gas over water. And it's very easy. We just subtract out the water vapor pressure. And there are tables that have the water vapor pressure at a specific temperature that you just look up. And most of the time, those tables can be listed in atmosphere, millimeters of mercury, torr, and kilopascals, so you don't even have to convert. You can just find the right table. So an example of that would be a gas collected over water at 8 degrees Celsius in a 350 milliliter vessel has a total pressure of 634. So that 634 torr includes some water vapor pressure. So we would need to subtract that out, and it gave us the water vapor pressure. So to get the dry gas, we would say, you have to hit the button to make it want to. I do that all the time. It makes me so mad at myself. So we do P of the dry gas. So we would just take the 634, subtract the 8.1, and then we would get 626 torr. That would be our dry gas pressure. So basically you have to correct for the volume. For the pressure. Okay? Any questions on Daltons? That's pretty straightforward. If you can add and subtract.
Yeah, we don't have 8.1.
It's at the very, very bottom of that page. Yeah, most of that is explaining the process of collect. That's because I looked it up for you. There you go. So write that down so when you go back and look at it, you don't go, oh, where did that 8.1 come from? So in parentheses, write vapor pressure of water is 8.1 torr at 8 degrees Celsius. And I looked that up. I didn't make it up. I didn't memorize it. I just went to a table. Actually, I probably asked Siri, what is the water vapor pressure at 8 degrees Celsius? Yeah. I don't know if she's that specific, but she might be. I don't know. Y'all can try it later. So that brings us to the bulk and the meat of our lesson today, which is the ideal gas law. Okay? The ideal gas law, it looks like this. It has lovingly been called for years and years by chemistry students as PIV-NERT. Okay? PV equals nRT. P is pressure, V is volume, N is number of moles, and R is your gas law constants, which we will discuss in a moment. And then, of course, T is temperature. And when we're doing gas laws, temperature always has to be in Kelvin. Every single time. So the ideal gas law is actually derived from 3 laws, and that is Boyle's, Charles, and Avogadro's. So fill in your blanks. Boyle's, Charles, oops, that L, and Avogadro's law. Okay? So, in reality, an ideal gas actually does not exist. Okay? It is a theory, kind of like the kinetic molecular theory. But we are going to assume that these gases are behaving ideally. That's why we use these gas laws, because they're a decent assumption. It's going to make our math easier, and it's a closer approximation. But this is something you do need to know, and we'll highlight it. Real gases behave like ideal gases at high temperatures and low pressures. Also, nonpolar molecules will behave more ideally. That's important. I would put a star by it. Okay. So why do you think that real gases behave more like an ideal gas at these conditions of high temperature and low pressure? You got any theories on that? Why a gas will behave more ideally at high temperatures and low pressures? Think about in terms of the particles and their relationship to each other. If you're at high temperatures and low pressure, how are the particles? Well, why wouldn't they interact with each other? Where are they? They're spread out. They're very far apart. So if they're very far apart, they're not going to interact with each other as much. Okay? And in the case of nonpolar molecules, why would they behave more ideally? They don't have an attraction for each other like they would in a polar molecule. So that's going to be important. Put a star by it. Okay? So that brings us to R. How do we get R, the ideal gas law constant? Okay, you get that from the standard conditions. 1 mole of a substance, 1 atmosphere, 22.4 liters per mole, and then 273 K at standard conditions. So if you put all that in there, you get 0.0821, excuse me. Sometimes you'll see it as 0.08206, which is an accepted value too, but for our purposes, we round to 0.21, so it's easier. And your units are liters, atmosphere, mole, K. That means when we're using the ideal gas law, all of our pressures must be in what? Atmosphere. All of our volumes must be liters. And then any kind of amount would have to be in moles. And then, of course, just like the other gas laws, temperature has to be Kelvin. There are other gas law constants. There is a value if you wanted your pressure in torr. There is a value if you wanted to keep your pressure in kilopascals. But over the years, we have found it's just easier to use the 0.0821 and convert everything to atmosphere on your pressures. Makes it easier. Less mistakes, because then people start confusing the numbers and then they use the wrong gas law constant with their long pressure. So just convert everything to atmosphere. It's an easy conversion, quick and easy. Okay? So let's use a couple of examples. So it says, what pressure will be exerted by a 0.4 moles of gas in a 10-liter vessel at 27 degrees Celsius? First of all, the way that you can recognize, like especially on the test, because you're going to have problems all mixed in, the way that you can recognize that it's an ideal gas law problem versus one of the other basic ones is that there's nothing being changed here and you have to find the new condition. So when we're doing boils, they would give you maybe they give you 2 pressures and a volume and say, hey, what's the new volume? Or they'll give you 2 temperatures and say, what's the new pressure? They were changing something and wanting you to find what the new or the original was. In this, there's nothing being changed. Just going to give you 3 out of the 4 variables that you need and ask you to solve for the other one. So that's a way you can recognize which formula to use. And you do have to memorize PIV-NERD for the test. Okay? Shouldn't be hard. It's PIV-NERD. Okay? All right. So what pressure will be exerted? So we're going to start with PV equals nRT. We are solving for pressure, so it's going to be nRT over V. Okay? First things first, convert to Kelvin so that you don't accidentally put Celsius in there. All right, and then you say this is V1, or it's not just V1, it's just V, and then this is N. So now plug and chug. Throw it all in there and put it in your calculator. So we have 0.400 moles. We have our R value, 0.0821, liter atmosphere, mole K, 300 Kelvin divided by 10.0 liters. So let me show you, moles are going to cancel, liters are going to cancel, and Kelvin is going to cancel, which leaves us with our unit of atmosphere, which is good because that's what we want. So we throw that in the calculator, and we should get 0.985. That should have been a 300. Everything has 3 significant figures. Never use your R value to determine your sig figs. Why? It's a constant. Correct. We don't use our constants to do that. Okay? So far, so good? Does anybody have the sig figs? Okay, so remember I said yesterday for sig figs and temperature, when you add 27 and 273, right? You're not looking at your total sig figs there. You're looking at decimal points because you're adding. Remember when we add? So when you add it, it should have no decimal points. So we should assume that that's 300 point, and I forgot to put the point when I did up there. So when I do that, it should have 3 sig figs. Okay? It just so happens that everything else has 3 sig figs as well. Okay? I'm not as hardcore on the sig figs on this unit because the temperature thing gets confusing for some kids. And I don't believe I told you, I haven't made this decision, so don't hold me to it. But I am leaning heavily towards a all multiple choice test for this unit. Because I'm tired of the last 3 tests have been a booger to grade with all that free response. So I'm leaning towards it, okay? But I'm not making any promises. It kind of has to be somewhat short because you have to have time to do the calculations, okay? But you need to be able to do the calculations quickly, though, okay? So this one, it says a sample of methane gas contains 1,500 liters at a pressure of 15 atmosphere and a temperature of 45 degrees. How many grams of methane are in the sample? Can I solve directly for grams? No, I cannot. What can I solve for, though? Moles. And then what can I do? Convert how? Molar mass it. Right. Okay. So I want to say 45 plus 273 is how much? 318? You were close. All right, so we're solving for moles this time. So we should have N is equal to PV over RT. So let's plug it in. So we have 15 atmosphere, 1,500 liters. So I should expect a really big number or a really small number? Big. 1,500 liters is a lot of gas. Your RT, 0.0821 liters atmosphere, mole K, and then our temperature was 318. Everything cancels out except for moles. And when I do that math, I should get 862 moles, which is a lot, which is what we expect. And then I can just throw in the molar mass of CH4. And with 3 significant figures, I should get 13,800 grams of CH4, which is a lot of methane. Okay? Any questions at this point? Are we all good so far? Because if you don't ask questions, I'm assuming you understand it. Now we have applications of the ideal gas law. So you can take that ideal gas law and you can derive some different equations that are going to be handy to you. The first one is for solving for molar mass. They might ask you to solve for the molar mass of a gas. I did not make this up. I mean, I know I make up silly and crazy and goofy things, but I can't take credit for this. But there's an equation that they call the molar mass kitty cat equation. Because how many of you have cats? Okay. Because they call it this because when you have to mark that. So they say this because when a cat goes to the bathroom, it meows and then it puts its dirt over its pee. So they call it the molar mass kitty cat equation because it puts dirt over pee. So I didn't make it up. I'm just telling you, it helps kids remember it. I say use the dirt over pee equation. Okay. So, and then you can rearrange that to solve for density and say that density is equal to the molar mass times pressure over RT. There's not one made up for that, so feel free to try one of your own. Okay? In order to do these equations, you need to first of all remember that density is equal to mass over volume, because sometimes they may not give you the density, they may give you a mass and a volume, and you can figure out, and that molar mass is equal to grams over moles. Okay? So you got to remember those two to be able to do that, which we've already learned, so hopefully you do remember that. So let's do a couple of examples of that, and then we're going to call it a day for notes. All right, determining the molar mass. If the density is 2.75, 729 torr, and 60 degrees Celsius. So first thing I need to do is do my temperature. Get in that habit so you don't accidentally put in there. So what is 60 plus 273? 333 Kelvin. I also noticed that I'm in torr. Can I use the R value in torr? No. So we're going to convert that real quick. 729 divided by 760 is 0.95, right?
Sure.
Okay. Sounds good to you. 0.959. That makes a difference. Okay? So now we can use our dirt over P. Molar mass equal to dirt over P. They gave us the density, so 2.75. grams per liter. Our R value, 0.0821. Our T, 333, divided by our pressure, which was 0.959 atmosphere. Liters cancels, mole does not cancel, take that back. Atmosphere does cancel though, and Kelvin cancels. So what I'm left with is grams per mole in my units, which is good, because that's what I need to have for molar mass. And then when I throw all that in my handy-dandy calculator, I get 78.4 grams per mole. I'm going to skip the next one. If you want me to give you the answer to it, I will, so that you can calculate it and see if you get the correct answer. The answer to the next one is 494.71 grams per mole. So I would encourage you to try that, because that one's got some, you're going to have to convert kilopascals. They give you a gram and a milliliter, so you're going to have to convert to liters and then solve for density. Okay, so that's a hint for that one. The next one, this time we're going to solve for density. So I know that if I'm going to, what is the density, I'm going to need this formula. Density is equal to the molar mass times pressure over RT. But do I have a molar mass here? I do not. They're not giving me outright a molar mass. Do I know what gas I have to go look up the molar mass? I do not. But what do I have? I have grams and I have moles. So I can say molar mass is equal to 15.9 grams divided by 3 moles, right? Which would give me 5.30 grams per mole. So now I can throw that in my equation. So 5.30 grams per mole. We have the pressure, 2.31 atmosphere. We have our R value, 0.0821. And we have our temperature of, oh, look there, they already gave it to us in Kelvin. So I cancel out moles, I cancel out atmosphere, I cancel out Kelvin, which leaves me with a unit of grams per liter, which is the unit for density. So I do that calculation. Looks like I need 3 sig figs from all that mess, and I get 0.479 grams per liter. Would you have thought of this step on your own? No, that's why I showed you. So in the problem above that I said I gave you the answer to, but I didn't work it out, you will have to do that with density. They give you grams and liters, so you'll have to calculate a density and throw that in the equation. So sometimes they do that. Okay? Any questions? Nope. I'm not going to do the next one, but I'll tell you that the answer to the next one is 1.56 grams per liter if you want to try to work it out. And then, of course, you have your examples in the notes that I already gave you the answers to, but that way you know if you can work it out correctly.